Click those all the way closed, please. I want to show you something in here. It's going to be very helpful to you. Okay, so I'm going to give you a handout here in just a little bit. Here's what the handout's going to say. So we want to, tell you what, in fact, let me just print out a couple, and I'll give it to you right now. Doing lots of stuff, compound transformation. So we want to be able to take a parent graph and translate it and do vertical reflections and or dilations. Okay, so what's that mean? So then if we're going to try to come up with a sketch of this graph, first of all, what's the parent graph? We got to always compare it to the parent graph. So we've done a bunch of stuff to this, but where would we have started at the most simple function that has those characteristics?
It deals inside the value.
Okay, it's an absolute value function, isn't it? And then we're doing stuff to an absolute value function, but the most basic. So click and close, please, all the way. Let's see. I don't want to see any Chromebooks open for a second here. Everybody's got to be watching this, because this is. I can make this relatively easy, but if you don't get this in here, it's going to be hard. I mean, there's a lot of stuff going on, and you really have to carefully organize the way you look at this stuff, or it's going to be complicated. So you got to really. This is one of those times when you got to just discipline yourself to really focus and try to take all this in and go through a couple examples with me. And then we're going to have you try it right away, and that's how you're going to learn this stuff. So we want to start with the most simple possible version of this graph, and then we'll tweak it to do all these things to it, right? So that is an absolute value function, right? So if we write in y equals, or we'll call it p of x. We'll just call it p for parent. P of x equals the absolute value of x. So we want to know what is the basic parent graph? What does it do? What does it look like? So if I were just to graph p of x, what does an absolute value function look like? Okay, it's going to be a v with a vertex at the origin, right? So the coordinates of our special point, which we call a vertex here, are just 0, 0, right? What are some other points on the graph? Like if I went over 1 to the right, how far up would I go?
1.
1. Okay, so I know it's going to go through the point 1, 1. If I went over, let's just say if I went over 4, how far up would I go? 4, right? This is just a line with a slope of 1. Right, so however far I go to the right, I'm also going to go that far up. Those are all points that I could use to describe the function. If I go backwards, it's going to be the same thing, isn't it? It's got symmetry about the y-axis here, folding symmetry. So if I go back 1, I'll still go up 1. If I go back 4,
You'll go up 4.
I'll go up 4, right? So that's the parent graph that we're going to tweak like this. Okay, so there are a couple ways we can do this, a couple ways to think about it. Now you could think about doing this as a bunch of transformations, right? And that's fine. The way the book talks about this in the reading, the required reading for this stuff, is just, it tells you we're going to do the dilation and the reflection first. Okay, so if I take the absolute value of x and I multiply by -1/4, what are the two things that are going on?
It's going over the x-axis.
Okay, it's getting reflected vertically, right? And what about the 1/4 part?
Compressing it.
It's compressing it. Okay, now let's look at this. I want to go to Desmos and study this a little bit, so you guys really see all these relationships here that we're talking about. Where is my? There we go. Okay. Okay, so if I look at this graph right here, does everybody agree there's our absolute value function, right? And it goes through, like we said, it goes through the point over 1, up 1, over 4, up 4, back 4, up 4. How do we get those points? Well, one way we can do it is by just evaluating the function at those places. If I input a 1 for x, what's the output going to be? What's the absolute value of 1? 1. So we get back 1 for y. If I input a positive 4, absolute value of positive 4 is positive 4. If I input a negative 4, absolute value of negative 4 is positive 4. So it's no mystery how we get all those points then, right? Okay, so now though, we want to do a couple things. Let's write f of x, and let's do two things to this. Let's take our absolute value function, and we're going to do two things to it. We're going to, first of all, let's multiply by 1/4. Okay, so if I multiply by, look what that does. Let's change the color here too. Let's make that blue. How about? Okay, so now, what points is this going to go through? So let's find some points here. Well, if I input a 0, what am I going to get back from my y value? What's the absolute value of 0?
0.
Times 1/4?
0.
No. Oh, 0, right, sorry. You're right. So 0, comma, 0, right? So there's one point it goes through. You're right. What if I input a 1, positive 1? What's the absolute value? I got to do 1/4 times the absolute value of 1. What's the absolute value of 1?
1.
1 times 1/4?
2. 1.25.
Well,
Yeah.
1/4 times 1? 0.25 or 1/4? Right? There it is. Okay, that's on the blue curve like it should be. If I input negative 1, I should still get back the same thing, shouldn't I? Because 1/4 times the absolute value of negative 1 is still 1/4.
Yep.
Let's do one more. If I put in positive 4, what am I going to get back? So 1/4 times the absolute value of 4 is 1. 1/4 times 4 is 1, right? Good. And then, okay, I'll tell you what, let's put one more. If I put in negative 4, I still get back 1. Everybody agree?
Mm-hmm.
Okay, so we see that the 1/4 part, and this is the part I really want you to get here. We call that a dilation, a vertical dilation. Dilation means we're either going to stretch or compress vertically, right? So what used to be, how could we, okay, what used to be a distance of 4, a vertical distance of 4, we multiplied by 1/4, and we got back instead a distance of 1. So what does that mean? Well, we've just compressed that down, so it's only 1/4 as high as it used to be, right? It's going to be that way for all of the points. Why do you suppose I picked 4 as a point? Because it's divisible by 4, right? We want to pick, when we're doing a problem like this, where the value of A is the absolute, let's not worry about this, the negative sign, is 1/4. I want to pick, that means that we're going to compress the function by 4. It'd be nice to pick convenient points whose y values to start with for the parent function are multiples of 4, right? So I could go over 4 and then, whoops, and then that's convenient for me because if I go over 4, I've got a y value of 4. I could also maybe go over 8 and have a y value of 8. That would make sense too, right? Those are easy numbers to multiply by 1/4 to compress the y values. Does it have to be that? No, it doesn't, but it's just way more convenient. If we look at, like, for example, this point right here, when I went over 1, well, 1 times 1/4 is 1/4. That's a hard point to graph. It doesn't fall at a convenient place on the graph paper, right? You see that? Okay, so then the last part of this is if I were to flip the function around. So let's make it, let's make a new one. let's call this g of x, and it's going to equal, start off with that. Let's change the color. Let's make it green. About. Okay, and if I multiply also by -1, look what it does. As expected, it's going to reverse that function around. Okay, there's an easy way we can do this one too. Easy way that we can spot the points. We can combine the compression and the reflection, and here's how. If we make some ordered pairs, what's going to happen if I put a 0 into g of x? -1/4 times the absolute value of 0 is 0. Okay, so there's the point. Oh, let's make this green so it matches the function. There we go. Okay, what if I put in, for example, a +4? -1/4 times the absolute value of 4 is, what's the absolute value of 4? What's 4 times -1/4? -1. Voila. Look, we just jumped right from the red to the green then, didn't we? Right? If A is equal to -1/4, then we're going to multiply a convenient y value, like 4, by -1/4. What's that tell us? Well, it tells us a couple important things. It tells us it's compressed because now instead of being 4, it's only got a distance of 1. It's only going to be 1 away from the x-axis, but it's negative, so it means that we're going down. Right? Everybody get that? Okay. So one thing we could do is we could, if we're going to try to create this function, right, is we could start with that green one. We could go ahead and do the dilation and the reflection first, and then we could take care of the translation part. What are we doing if we're adding 5 to the whole thing? Moving it up 5. Okay. What are we doing if we're subtracting 3 from x, from the input? Going right by 3, right? So we could do this in discrete steps then. We could go, let's go ahead and get rid of, we don't really need this guy anymore. But if I start with the green one here, now if I want to take that green function and I want to translate it, all I'd really have to do, let's call this h of x, I guess. And we're just going to say we're going to borrow this function, so it's going to look just like this one. But if I subtract 3, look what it does. It scoots over 3 from x. It scoots to the right by 3. What was the other part? I added 5. Is that right?
Yep.
There it is. There's my function. Does that make sense? Yeah, because we turned the red to the green by applying the a value of -1/4. Reflected and dilated, and then I translated the function. Agreed? Okay? Here's what I'm going to suggest, though. I'm going to suggest that maybe we didn't even have to do both of those steps. What if we had just done this? What if we had just started with our parent function, right? And we had done this in the opposite order. We had said, okay, based on our conversation yesterday, we know that if we have a function like this, if it's in this form, it's telling us, sure, it's telling us about a translation, but the special point called the vertex that started at the origin, if I do this kind of a translation, really these numbers, instead of thinking of it as a translation, just think of it as the coordinates of the special point. It's where we're going, that's where our function is going to be anchored, right? So we would know that if we look at this, we would say, okay, h is 3, that's the horizontal translation. But we recognize it as the x-coordinate of the vertex is 3, and the y-coordinate is 5. So right away, that tells us that our function is going to be anchored with a vertex at +3, +5, right? Okay, now what about the -1/4 part? Well, the -1/4 part, really all that's doing is it's saying, let's go ahead and turn these off too. Oops. Yeah. Really all that's saying here is that if I want to take this parent function and dilate it about its vertex, this is what we end up with, right? The parent function, remember, just looks like this. Okay, we already know that that's our starting point. Let's pick some convenient points. Instead of going over 4 and up 4, let me redraw that. So this really is good, so it goes right where it's supposed to go. Instead of going over 4 and up 4 from the vertex, right? Instead of going over 4 and up 4, we're going to go over 4, and we're going to go vertically negative 1/4 times 4, right? From our starting point. So from here, we know that negative 1/4 times 4 equals negative 1. So we're going to go over 4 and down 1 to get to another point other than our vertex. And then all we'd have to do is just start at the vertex and pass through that point on forever. On the other side, we would just do the opposite, right? Because we have that kind of symmetry. If we went over 4 and down 1, then we must also go back 4 and down 1 so we get that folding symmetry, right? And we can do that really in just one step, right? We can start with a function like this, and we can say, okay, where's our special point? And then how are we going to reflect and dilate the function from there, our parent graph? Everybody see that? Okay. So if we wanted to, okay, let's try one of these then. I want you guys to try one of these. So open up your Chromebooks and go to 2.2 practice 2. And here's the one. So everybody do, and I just want to see that everybody gets this right. So go to, here we are, Unit 2 practice. If you go down, I want you to try this one. 2.2 practice 2. It's called vertical reflections.
What about the other one?
I skipped that for now. You'll go back to that. But if you can do this one, that one's going to be a piece of cake. Okay?
Vertical reflections.
Yes. And go to group 3 and just do a problem from group 3. So you're going to get something like that. Okay, and I want you to choose the correct graph based on that absolute value function that they give you. And so the way I'd like you to do this, at least the first time, is instead of just picking a graph, I'd like you to sketch that graph. Okay, find the anchor point, find the vertex, and then apply the reflection and dilation. Okay, and then pick the graph that matches what you have. So if you need graph paper, I've got good graph paper here. This is awesome graph paper for this kind of thing. So if you need some, help yourself. It's right here. So everybody try one of these, and then we'll go through one more together.